In order to get where you're going, you should probably know where you came from. So this video is all the history of chemistry. Now, it's not important that you know any of the dates. It's not as though they're going to say in what year did Rutherford do his experiment, but you do need to know who some of these people are and where some of these concepts come from. So you need to know more the sequence of events, not so much the timeline. So with that, let's go ahead and get rolling. The earliest known records of anyone doing any sort of chemical work is about 1000 BC, when people started processing ore to produce metals and weapons. And it's not until about 400 BC that the Greeks actually proposed calling these materials something. And they came up with the fact that there are 4 elements: earth, air, fire, and water, which come together give you Captain Planet. Democritus was one very notable Greek, and he said that those elements are made of atmos, which he described as the ultimate smallest particle of matter, the smallest of small amount. So he coined the term atoms. I'm going to have to move this so it's easier to access. Okay. And then for the next 2,000 years, we entered this dark ages of chemistry, where alchemy reigned, which was this make-believe pseudoscience mysticism, where everyone was convinced that they could turn metals into gold. And there was a lot of mistakes. A lot of people did some very silly things. The Romans drank out of lead goblets, which gave them lead poisoning. But there was some good science that came out of it, mainly a lot of your aromatics, so a lot of perfumes came from alchemy. But it's a time period where a lot of chemists don't really want to talk about, so we're going to move on. In the 16th and 17th century, we actually start seeing a boom in actual chemistry. The first is George Bauer, or Geoff Bauer, is German. He refined the process of extracting metals from ores. And a guy who is Swiss, whose name I cannot pronounce, so let's say it's Perseus. We're going to pretend he's Greek, apparently. Used minerals is credited with using minerals for medicinal purposes. But someone we all know, and is actually attributed with a lot of things in chemistry, is Robert Boyle, like Boyle's Law. Robert Boyle was a balloonist, which means he liked to go up in hot air balloons, and he actually did quantitative work, meaning he took numbers and left data that can later be developed. And he did quantitative data on pressure versus volume. So if you remember from Baby Chem, Boyle's Law, well, this is the Boyles we're talking about, or this is the Boyle we're talking about. He also gave us a working definition for what an element was. More than just earth, air, fire, and water, he actually gave us, well, there must be some component to it. Now, also in the 17th century, industrialization was starting to go on, so people started to work on, look at combustion a bit. Not as much, but late 17th century we're talking. And a guy by the name of Stahls, who was another German, suggested this thing called phlogiston, which was this mythical element that flowed out of burning materials. And when you put a candle into a closed container, the reason it went out was because the phlogiston saturated the air. Well, a guy by the name of Joseph Priestley came along, and he actually discovered oxygen. Believe it or not, people had to discover stuff like oxygen. And he said, no, the reason that the candle goes out isn't because of excess phlogiston. It's because of oxygen. So he disproved this make-believe thing called phlogiston. Again, you're probably never going to be asked, what was this mythical phlogiston? You may just be on Jeopardy one day. So, for your information. No. There we go. In the 18th century, industrialization was at its full blast, And so combustion was looked at a lot because combustion is what drove a lot of that. So we did a lot of work with carbon dioxide, nitrogen, hydrogen, and oxygen. And the list of elements that people knew about began to grow. So a lot of the periodic table started to come about. And we're going to do a whole video on the periodic table history later, but for right now, this is the time frame when it would start happening. So the first thing that came out of this industrialization of chemistry in the 18th century was Antoine Lavoisier, or Lavoisier, a French scientist who looked at combustion and explained how it happens, what happens when something undergoes combustion, when something burns. And he actually published the first textbook on chemistry, and in that textbook he stated the law of conservation of mass. He saw that when you burned a candle, the residue on the candle, on the glass that the candle was in, was comparable to the amount of mass that the candle lost. So he said, well, that means that the matter is not necessarily destroyed, it's just changing form. So the law of conservation of mass is simply that matter can be neither created nor destroyed. Later in that same time frame, a scientist by the name of Proust gave us the law of definite proportions, which simply states that a given compound always contains exactly the same proportions of elements by mass. Now, it's a fancy way of saying that the table salt on your table is the same as the table salt on someone's table in Japan. That sodium chloride is always sodium chloride no matter where it's made or who does it, because they have to combine in equal proportions. In 1808, John Dalton gave us the law of definite proportions, which he later went on to develop the atomic theory. But the law of multiple proportions simply states that when two elements combine to form a series of compounds, like say carbon monoxide, carbon dioxide, the ratio of masses of the second element that combined with 1 gram of the first element, so the ratio of oxygen to carbon in that series, that combined with 1 gram of the first element can only be reduced to small whole numbers. Law of multiple proportions simply means that you cannot have half of an oxygen atom. It's carbon monoxide, meaning CO, carbon dioxide, CO2. There is no carbon 1.5 oxides. They're always whole numbers. He also gave us the atomic theory of matter, which simply states that, and this is based on at the time, so there are a couple little sidebars that we need to take note of, and we'll go to those in a moment. Atomic theory of matter states that all matter is made up of atoms which cannot be broken down further. We now know that that's not necessarily true. You can break an atom down into the parts of an atom, electrons, protons, and neutrons, and even those we now know can be broken down even smaller into quarks. The atomic theory also states that all atoms of a given element are identical in both mass and chemical properties. Again, this is partially right. All atoms of a given element are identical in chemical properties, however, not in mass. Because elements can differ in mass. Those are called isotopes. And they have the same number of protons but different masses because their number of neutrons is different. Compounds are formed by the combination of different elements in small whole number ratios. That is also true. A chemical reaction involves only the combination, separation, and rearrangement of atoms. You cannot take an atom and change it into something else. You can take a compound and change it into something else, but the atoms are always going to be the same. They will just rearrange, separate, or come together. In the 16th century, we now have a lot of balloon stuff going on. People are very interested in some chemical processes. So chemistry is in its height at this point. And the first balloonist that gave us some new discoveries was a guy by the name of Joseph Gay-Lussac, a Frenchman, who performed experiments on gases at the same temperature and pressure but at different volumes and how they reacted with one another. And he found that, or based off of his work, Avogadro, yes, the guy who gave us the mole, if you remember from Baby Chem. If not, don't worry, Avogadro will be your new best friend. Avogadro used his work to propose his hypothesis on the mole, because before he published anything about the mole, he did work on gases. And his hypothesis was that at the same temperature and pressure, equal volumes of different gases contain the same number of particles. So 1 mole of any gas at standard temperature and pressure is 22.4. That's where that came from. The first theory on what an element or atom looks like came from a man by the name of Thomson, or J.J. Thomson. He was an Englishman who worked with vacuums. Or the best vacuum he could make. He sucked all of the air out of this glass tube, and he found that when he shot an electrical field through it, or he passed an electrical field through it, it produced light at the end on a fluorescent tube. He called this a cathode ray. And no matter what material he put and then passed the electricity through, it always gave off this negative energy. And he knew it was negative because when he when he put a magnet to it, it curved. So he said all elements and all matter has some negative component, which he termed an electron. And this is a very, very, very simple diagram of a cathode ray. It's called a cathode ray because the point of origin for this ray is in the cathode. And you can see that it bends towards a magnet because it is negatively charged. If the magnet weren't there, it would just shoot across towards the anode or towards the positive end. So he said, well, since all atoms have this negative component, they must also have a positive component, because it's not like you walk around and touch a cable and get shocked. They must cancel each other out somehow. So he said, well, the atom must look like plum pudding. Now, English people call everything pudding. Plum pudding is actually a bread with some raisin stuff in it. So it actually looks like this. And he said, this is what an atom has to look like, because it has these negative things, which would be these raisins in it, surrounded by this positive energy. So the plum pudding model was the original model for what the atom actually looked like. And again, that was based off of the work of J.J. Thomson. Now that theory held together for about 100 years, and in that time, a guy by the name of Robert Millikan, the first American to do some work on this, he found out the mass of those electrons, and the way he did this was actually kind of ingenious. He put two plates opposite one another, positively charged and negatively charged plate, and he took some oil and sprayed it over the plate so that only one droplet could fall down between the two. And he found that if he balanced the attraction from the positive to the negative plate, if he held that one droplet of oil together, or in the center of it, he could find the mass of the electrons in it by ionizing it. So it was rather ingenious what he did. But you can always keep in mind, Robert Millikan worked with an oil can to find the mass of an electron, and he found that it was really, really, really small. It was 9.1 times 10 to the minus 31 kilograms. Even on the scale that you memorized from the previous videos, that's on the order of, that's 9.11 times 10 to the minus 19 nanograms. So we're getting even smaller than what I had you memorize. In fact, if you look at your notes, I don't believe you go past negative 12, so we're going even smaller than the smallest unit you have or that you know. In the 19th century, some people did some other interesting things. Berquell found out that uranium produced an image in the dark, and he called this radioactivity. So let's talk a little bit about radioactivity. And I just lost my place. There we go. And then oil can back over. Okay. Berquell, again, found that discovered radioactivity. Didn't live long because of it. So there are 3 types of radioactive decay, and we're going to go into these in much greater detail when we talk about kinetics, but you just need to know some basics of them for this first test, or for this first unit summer review. Alpha decay is the largest of all the radioactive decay, and therefore it is the least harmful because it has the least amount of energy, because it's really big. It doesn't take a lot to stop it. It's equivalent to a helium atom, because it has, or a helium nucleus. It has 2 protons and 2 neutrons, so it has a mass of 4. Typically, just a piece of paper is enough to stop alpha decay. Beta decay comes in 2 varieties. It can be positive or negative, but it's the equivalent in mass to an electron, so it can penetrate a lot further because it's a lot smaller and travels a lot faster. You would need typically about a sheet of aluminum. In baby chem, we say a piece of cardboard. It can be stopped. Again, doesn't take a lot, but because it has a pretty sizable mass, and doesn't have as much energy because of that, and that's beta decay. Gamma radiation has no mass whatsoever. It's pure energy, pure photonic energy, and it is extremely dangerous. This is the stuff that causes you to have cancer and leads to all sorts of problems with the like nuclear power plants. This is the thing people worry about, because it would take a sheet of lead to stop gamma radiation. Lead being very dense can block a sizable chunk of that energy. When you go to the dentist and they're taking those x-rays of your teeth, the reason they leave the room and put that lead blanket over you is because they're bombarding you with a minute dose of gamma radiation, which we found out in the 19th century produces an image in the dark. Now, in the 19th century, the biggest thing in chemistry came along, or what I consider the biggest part, or the most important. It gave us our current understanding of the atom. A man by the name of Ernest Rutherford, an Englishman, wanted to prove the plum pudding theory. So he had his assistants take a piece of gold and he flattened it out as thin as possible. Now, gold is extremely malleable and can be flattened, is easily bended and folded. That's what malleable means. But it also can be hammered down. It's very ductile. It can be hammered down into very, very thin sheets. And he hammered it down to 1 or 2 atoms thick. I think it was like 3 at the most. It was actually very, very, it was very good for that time. And he had his assistants shoot some alpha radiation, which remember is the size of a helium atom, at this thin sheet. And he surrounded that thin sheet with this screen that detected those alpha particles. It would light up when it had those alpha particles hit it. And they recorded where those light ups occurred. Now, ideally, he said, I'll be able to fire these alpha particles, which travel at an immense speed. They'll shoot straight through it, and this will prove that the plum pudding model makes sense, because big atom hits big atom, they should both fly straight through. Well, he sets up his plan, and it looks something like this. He sets it up, and yes, a large number of the alpha particles make it through. However, a pretty decent amount actually bounced off or were deflected around that gold foil. Either went through it and bounced off of something inside of it, or reflected completely back. And he said this was the equivalent of shooting a howitzer, which is those artillery guns from World War II, at a piece of tissue paper. Or sorry, it's not the artillery guns, it was the machine guns. Shooting a machine gun at a piece of tissue paper and having it reflect back. Because it made no sense that this big honking atom through this little teeny amount is going to bounce off anything. If anything, they should have all made it through. And he got really mad at his assistants, and he actually may have fired them or rehired them when he found out he was wrong. But what this proved was that the atoms were passing through this thin space, but they were hitting something extraordinarily dense in the center and bouncing off of it or being reflected by it. So he said, well, that must be in the center of the atom, and it must be extraordinarily dense. So he stole the term nucleus from biology, the center of the cell. He stole that from biology, and he said, well, there must be a nucleus to the atom. And because these atoms were being deflected by it, some of them were just curving around it, it must be a positively charged center, because that would account for the positively charged opposite of the electrons. So he gave us the nuclear theory of the atom, where an atom is mostly empty space with electrons around it and a dense center which has a positive core. His assistants, after Rutherford passed away, went on to study this model of the atom, and he found that he was only coming up with half of the mass he was supposed to. So he hypothesized about there being a neutral component to the atom, and that's where we got neutrons from. So that all came together and came before our understanding of the modern view of the atom.